Hi class, today I want to talk about equations that are used to solve motion problems. So we've been using this average velocity equals displacement over time, and average velocity we know when we're steadily increasing our velocity, our average velocity is right in the middle of our starting velocity and our ending velocity. So if we started out, if our initial velocity was, let's say, 20 meters per second and we ended up at 30 meters per second would be our final velocity, we could easily find our average velocity, right? If we started off at 20 meters per second, we ended up at 30 meters per second, we know average velocity is right in the middle, about 25 meters per, well, exactly 25 meters per second. And so figuring out average velocity by adding the final velocity plus the initial velocity and dividing by 2, right? 20 plus 30 would be 50. 50 divided by 2 is 25. We've been using that successfully, which is great. So this is one very important relationship. Distance equals the average velocity during average velocity that an object had during a certain time period times time. So distance equals average velocity times time. Average velocity is distance over time. The other relationship that we've spoken about is acceleration. Acceleration is how much our velocity changes each second. And we can figure that out by looking at a change in velocity between over a certain time and dividing it by the time. So for example, if our velocity changes by, let's say our velocity changed by, well, in this case, let's say our velocity goes from 20 meters per second to 30 meters per second. So it changes by 10 meters per second. And let's say that takes place over 5 seconds. So time would be 5 seconds. Then our acceleration would be 2 meters per second of speed change each second. So we can figure out our acceleration by looking at our final velocity minus our initial velocity. 30 minus 20 would be a change in velocity of 10. And if that occurred over a 5-second time period, 10 over 5 would be 2, indicating that our speed changed by 2 meters per second each second. Okay, so we've been using those two relationships successfully. Now, you're sometimes encountering some problems where it's difficult to solve because maybe they don't give us final velocity or time, and then it's difficult to use this formula. And in situations like that, it can be solved, but it would involve filling in all the unknowns, simplifying the equation, filling in all the unknowns in this equation, simplifying the equation, and then kind of solving a system of equations between the two. To simplify that, we created two new equations. And all these equations for example, this equation at the bottom does not have time in it. So the way this equation was created was we solved this equation for time, we solved this equation for time, and we basically substituted one into the other. Okay, I'll pause and do that math quickly. Okay, I'm back. So I took this equation, this is this equation up here. Okay, so average velocity equals displacement over time, and I took this equation, acceleration is change in velocity over time. I solved both equations for time. That's here. So this equation solved for time is here. This equation solved for time is here. Then I substituted. I said if t is equal to this, I'm going to replace t with what it's equal to. So I plugged that in for t, came up with this relationship, then just did some cross multiplication. 2d times a, 2d times a, vf plus vi times vf minus vi. Okay. Then I expanded this, and then I simply added vi to both sides to get the equation to look like this, which is simply this equation. Okay, let me pause that. Okay, so we just showed you that this equation can simply be derived by solving each of these equations for t, setting them equal to each other, and I get this equation. Well, what does that do for me? It gives me a new equation that does not have t in it. Okay, so this equation does not have time in it, and that'll be useful. Similarly, this equation over here is also simply derived. In this case, we solved both of these equations for VF. So we got VF all by itself. We got VF all by itself. We did the exact same process, set them equal to each other, simplify the equation, and we get this. So you say, okay, great. What does that do for me? Well, we now have an equation that does not have VF in it. And that's also useful for solving some problems. Okay, so we now, instead of having two equations that are very useful for solving motion problems, we now have four equations. And I'll describe how these four equations can be helpful. But let's summarize certain aspects of these equations. Okay. All right, so again, we've got our four main equations. Distance equals average velocity times time, acceleration is change in velocity over time, and these two equations down here, which were simply derived from these equations. What are the variables that you may be given in an equation? Okay, well, in all these equations, what are our variables? Or in all cases, what are our variables? We might be given displacement, we might be given final velocity, initial velocity, time, and acceleration. Now, as I said, with this equation that we most recently derived, it involves velocity, final velocity, initial. We can see those variables here. Acceleration and displacement, we can see those variables here. It does not have time, no time in this equation. This equation, which we also derived, has displacement, velocity, initial, time. You can see velocity, initial, time, displacement, acceleration. What doesn't this equation have? It doesn't have final velocity. All right, and let's go back to our original two equations. Acceleration is our change in velocity over time. Velocity final minus velocity initial over time. Well, what does it have? It has acceleration, final velocity, initial velocity, and time. What doesn't it have? It doesn't have distance or displacement in it. And our original equation, distance is average velocity times time. When we define average velocity as velocity final plus velocity initial divided by 2. Okay, what does this equation have? It has displacement, velocity initial, velocity final, and time. What doesn't it have? It doesn't have acceleration. So we've got four equations and each of these equations does not have one of these five variables that we will see in our motion problems. Okay, so this equation doesn't have acceleration, this equation doesn't have displacement, this equation doesn't have final velocity, and this equation doesn't have time. And thinking about it this way, thinking about it this way is a useful way for solving some problems, especially those problems where these two equations alone would be very difficult to solve equations. For example, if we're given a situation where we don't have final velocity or time, these equations are difficult to use by themselves. But we can use some of these equations to really make life easier. So one way to consider solving motion problems would be to say, hey, I've got four equations at my disposal now, not just two, four equations, these two that we've been discussing, and these two derived equations. And what would your problem-solving methodology be? Well, I call this the GRASS method, G-R-A-S-S, okay? List everything that was given to us with quantities, okay? List all the known variables with the units, okay? List them all out. Write down what's given. And write down what we need to find or need to solve for. That's very important as well. Then do the analysis. Choose the formula that we think is appropriate to use. Just kind of looking at it from this methodology. Which of these equations has the variables that we have and that we're given and need to find, and excludes the variable that we weren't given and also don't need to find. Okay? And then just go ahead and use the appropriate formula and substitute in the information and then solve the equation and state the answer with units. Okay, so write down the givens, write down the required analysis, which is basically figure out the equation, substitute all the numbers in, and solve and state the answer. All right, let's try some examples. Okay, so here we've got a truck with an initial speed of 12 meters per second. So there, we've just been given VI. So VI, so we're going to write that down, 12 meters per second. This is our givens. Okay, this is the G part of our GRASS method. Accelerates at 2 meters per second squared. So they just gave us acceleration. 2 meters per second squared. Okay, for 3 seconds. They just gave us time. Time. 3 seconds. Okay, what's required? what is the total distance traveled by the truck during this 3 seconds? They want to know the distance or displacement. Okay? So we're assuming straight line motion, distance, and displacement are going to be the same. All right, so now we know. Here are our 4 variables. What didn't they ask for or give us? Final velocity. That's what they didn't give us. So which equation doesn't have final velocity? This one has final velocity. This has final velocity. Change in velocity requires final velocity. Average velocity requires final velocity. But this equation here doesn't. Okay, so we're going to use that equation. That's our analysis. Velocity initial times time plus 1/2 AT squared. Alrighty, so we plug in what we're given. Velocity initial is 12, time is 3, acceleration is 2, time is 3 squared. Okay, and then we solve. 12 times 3 is 36. 1/2 times 2 is 1, times 3 squared is 9. 1 times 9 is 9, and equals 45. So our displacement is 45 meters. And boom, we have our answer. Now you might say, okay, I get it. You write down the variables that you're given in the other one, and you pick the equation and you solve it. But I could have solved this pretty easily just by figuring out final velocity, right? I could have pretty easily figured out final velocity from knowing my initial velocity, how much my speed is changing each second, and the time, right? I could have said I'm speeding up by 2 meters per second each second for 3 seconds. That's a 6 meter per second speed change. I started at 12 meters per second. So I could have pretty easily figured out my final velocity is 18 meters per second. And from 18 meters per second final velocity and 12 meters per second initial velocity, well, what's right in the middle of 12 and 18? Well, they're 6 apart. So if I go 3 up from 12 or 3 down from 18, I can figure out my average velocity pretty easily. And then I can figure out distance is average velocity times time, 15 times. The time is 3 seconds, and I could figure out 45 meters pretty easily. But what we just did, even though it was easy and logical, there were a few steps involved there. So sometimes it's easy just to take the formula and solve it all in one step. All right, let's do another one. Oops. There we go. Oh, that works actually. Oops. All right, let's just do this one. An object with an initial speed of 4 meters per second, that's velocity initial, 4 meters per second, accelerates at 2 meters per second squared. They just gave us an acceleration, 2 meters per second of speed change per second, in the direction of its motion, straight line, for a distance of 5 meters. What is the final speed? Sorry, no. So what's not here? Time, right? Time is not here. So which equation doesn't have time? Time. This one doesn't have time. So let's use that to figure out final velocity. Okay, so now we just did our analysis. Now let's do our work. So this equation is VF squared equals VI squared plus 2AD. And we're going to substitute everything we know. We know VI is 4. I'm going to leave off units for now. 4 squared plus 2. A is 2. Acceleration is 2. D is 5. Okay, 4 times 4 is 16. 2 times 2 is 4, times 5 is 20. So this equals 36. Okay, so VF squared equals 36. Let's take the square root of both sides. And we get 6. So our final velocity is 6 meters per second. And we have our answer. Okay, now this would have been difficult to solve just using our first 2 equations. It would have been very difficult to solve just using our first 2 equations. We would have had to set up a system of equations, and it would have been a real pain in the neck. But using these derived equations is very, very helpful. So I want you to consider this. Sometimes we can solve equations. A lot of times we can solve equations just using those same ideas that we've been using all along. distance equals average velocity times time. If we can quickly figure out what the average velocity was, this is a great formula for solving problems. And acceleration is change in velocity over time. So we can solve a lot of problems just using these two equations. Maybe we have to do it in 2 steps. Maybe we don't, but we can solve a lot of problems just by using these 2 equations. But sometimes you really have to use these 2 derived equations. And the method for doing it is, again, the graphs method. Write down everything that's given, write down what's required to be found, do your analysis, identify which equation is appropriate given those 4 variables, and then do your substitution and state your answer with units. Okay, graphs. So consider the graphs method when you are solving problems, but definitely consider these 2 new equations. They're very useful for solving many problems.